Sir, am I audible to you? Sir, are we audible to you?
Yes, I can hear you. Are you able to hear me?
Yes, sir. Good morning, sir.
Yeah, good morning.
Good morning, everyone. I am Pranati Purohit. I welcome you all to the morning session of the short-term course Power Converters for Green Energy and EV Integration 2024. Now the presentation will be addressed by Dr. Sanjeet Kumar Dwivedi, sir, Danfoss, Denmark, on the topic BEV versus FCEV, a comparative technological evaluation. Now I would like to introduce Dr. Sanjeet Kumar Dwivedi sir to you all. Dr. Sanjeet Kumar Dwivedi received the MTech degree with gold medal from Indian Institute of Technology, Roorkee, formerly University of Roorkee, India in 1999 and PhD degree from Indian Institute of Technology, Delhi, India in 2006. He joined Larsen and Turbo as graduate engineer training in 1991. In 1993, he joined as lecturer in electrical department, Government Engineering College, Sagar, MP, India, where he became associate professor in 2004 and HOD in 2007. Since October 2008, he is working as R&D engineer in Control Engineering Department of Danfoss Drives AS Denmark. His research interests include control methods of PM motors, induction motors, and synchronous reluctance motors, sensorless control of AC drives, energy efficient control of drives, and power quality. He is associated with the IEEE as senior member since 2009 and also served as technical editor of IEEE Transactions on Mechatronics. Now I request Dr. Sanjeet Kumar Dwivedi sir to address our participants. Over to you, sir.
Thank you very much, madam, for for your kind word and this introduction. So I welcome you all participants for this short-term course on power converter for green energy and EV integration and organized by E Department and IT Kerala. Please let me know if you can see my slide is changing and whenever you see I'm speaking and my slides are not relevant, and please ping me so that if there is any problem in transmission that can be, decide. So can you see that my slide is changed? Now I'm on the outline of presentation. There is a question. Can you hear me now?
Yes, sir, we are audible to you.
And then you see the slide outline of presentation.
Yes, sir.
Yes, sir.
Okay. So when I'm speaking and my slide and my speak that not matches, it happened that I am speaking and slide are changing, not changing. So please let me know. You can call me on WhatsApp or you ping me here. Thank you very much. And outline of my presentation is I will give you a short introduction and then why we need green hydrogen and then what is the green energy production status in world and in India. We will see some figure on it. Then green hydrogen, what is it? The statistics. Then we will move to how good hydrogen is as energy storage element. And, then later we evaluate for suitability for electrical vehicles. Then we'll see the characteristics of energy producing gases, volumetric versus gravimetric energy density. Afterward, we will look into value chain of green hydrogen system, production to end user, then role of green hydrogen for decarbonization of energy production sector and how hydrogen can help in different sector to decarbonize. Then $1 million question, why we need all electric transportation? What is the necessity of it? Then I try to bring you different perspective of battery energy vehicle and fuel cell based technical and engineering perspective, where we see performance based on energy density, based on its weight, based on it uh, mileage, and based on cost effectiveness. So we will see those conclusion in the end presentation. Then we will look into what need to be done and what is our responsibility in academia and industry, and how can we help to achieve it. Then key takeaway, question and answer, and when we close it. So I propose last 10 minutes we will keep for the question and answer. And Dr. Arnav and Sanjeet, please ping me when there is a 10-minute left and I'm still speaking and I'm involved in speaking. So I can cut down it and we can keep some time for open question and answer. So who am I? There is a very nice introduction given by Madam. So I will skip it most of the things. But I would like to tell you that I left Danfoss in 21 and I joined a green hydrogen-based multinational company, Everfuel, as a technology manager in 22. So 2 years I worked there, and my affiliation recently it is the adjunct professor in IITM Gwalior, and now I'm working as full-time senior consultant in Siemens Gamesa, that is offshore and onshore wind turbine wind plant manufacturer, one of the biggest in the world. And I'm working in a confidential project here, large single unit project. So, but this is my email. You can, after this presentation, you can reach me immediately or whenever you need, and you can also join me in LinkedIn if you. And nicely said by Madam, my field of interest and everything you know. So let's dive. This is my home place. It's known as Triangle Industrial Area, in the place known as Polding, where I'm living. And this is, this Siemens Gamesa, yes, Denmark. It's a multinational company. It is also having its one of headquarter in India too. And this here you can see assembly line of this giant stator of this generators, PM generator stator. They are making file and all those connector size you can see how big they are. And this is one of the largest. This is the nacelle, and it contains the turbine, the inverter, generator, the civil circuit, and this is some offshore plant. So the window of opportunity is closing fast for any meaningful action to limit planet increase in temperature and to counter the global climate crisis, and in order to make safe this planet Earth for our grandkids. There is a big alarming issue of climate change. If we see the global greenhouse gas emission and prediction for 30s, 40s, and 50s, United Nations in the Environmental Program, this emission gap report, then we will find that gigaton of carbon dioxide equivalent in 2030. If current policies are going on, then median is 56 gigaton. And if you want to keep estimated gap to least cost pathway consistent with limiting global warming, if you want to, we know this, there will be a still with that this gap will be 16 gigaton. Still, whatever measure we are taking, but we are not able to mitigate fully. But if we make little stringent target that we want to keep this temperature rise below 1.8 degrees centigrade, and in this gap is 22 gigaton. And similarly, if we go further, challenging goal with 1.5-degree average temperature rise, then it's 24 gigaton equivalent. And you see that this national uh, committed countries which are which already committed, unconditional committed and conditional committed countries. So unconditional, and they are having little more emission, and the goal is also the gas is also higher. And for 35, we see that still the gap is going to increase. So this predicted one is when there is a total emission is 56 gigaton equivalent, and for 50 is also this. But if we take action and current policy continued, then we see the gap will increase further and further. So we need our um, we need a coordinated effort in order to reduce this gap. And in a different perspective, if we see this the same graph in a different format, that 1.5 degree centigrade range or 2 degree centigrade range, with current policies, we see unconditional nationally determined contributor in this scenario. So conditional national determined contributor, we see that 11 gigaton equivalent emission is there. And if we lower side and higher side is 14 gigaton. And similarly, we see the median estimate for 1.5 degrees centigrade is 19 to 22. So we see that there is a this greenhouse gas emission is still, we are talking about to control it, but we need certain very strict measure for maintaining it. So if we look on how this, for EU perspective, you can look greenhouse gas emission target and required reduction. And if you look at this present scenario 22, it is megaton equivalent of carbon dioxide, that is 4,000, around 3,600 megaton, and there is a range between 3,000 to 3,700 and approximate. And until now, average last year 51, annual average emission reduction megaton carbon dioxide equivalent. But for next 6 years, it is we need to reduce it to 131 megaton equivalent. So you see how many 3 times more effort we need to take. What we did in last 8 years or 10 years, we need to do it that in next 6 years. And if you look different sectors, then you will find that transport sector that is having this 200 megaton equivalent carbon dioxide reduction target. And this is around 20%, 15 to 20% of overall power industry, building, agriculture waste, and land use change and forestry. So from different sector, transport sector is having a big, responsibility to reduce this greenhouse gas emission by around 20%. These are some global carbon dioxide emission sector-wise. When we are talking about power sector, industry sector, transport sector, and building, there is, you see, this one, this green one is 21, and this blue one is 20, and this one light blue, that's 2019. So all four sector, we see that almost from 19 to 22, carbon dioxide emission is, other than 20, that is quite in the same range, and it's a good sign that there is a reduction and it's not increasing, but we need to reduce it further. This is the prediction of greenhouse gas pollution due to light duty vehicle. It is in USA. Yeah, it's predicted until 21st, end of 21st century, and there are different scenarios. If we are not doing anything, then we are doing a billion tons of CO2 equivalent by 2100, and this we are making, whole environment we are polluting and not making safe for the future generation. If we go with the gasoline hybrid scenario, scenario get changed, and this is the current scenario. But how it is moving, you see that. And with comparing everything, battery energy vehicle, then you see this one, this scenario. And if you see hydrogen, hybrid electrical vehicle or internal combustion engine hydrogen based approach, then also we see a little improved scenario, because although efficiency is less, but pollution is zero, even with the internal combustion engine when hydrogen is used with the fuel. But the best scenario is the fuel cell, where we can achieve the greenhouse gas emission goal 80% below 1990 by 2070 and 60% below by 2055. And we can have uh, whatever our targeted goal by means of it. So this is the oil consumption prediction. Naturally, if we are not, we are moving away from um, electrical mobility, then we see that oil consumption is exponentially rises. And as soon as we go for the fuel cell electrical vehicle or hybrid electrical vehicle or plug-in hybrid electrical vehicle, this is going to reduce. So why green technologies, and why we need to look into it for e-mobility green technology? As you know, in 2015, due to Paris Agreement, nations around the world gather around and they agreed for rapid decarbonization is needed to prevent the dangerous impact of climate change. And in subsequently in 2018, the Intergovernmental Panel on Climate Change, IPCC, their report said global warming of 1.5 degrees centigrade shows that the need to cut greenhouse gas emission. And it is rapidly is even more urgent than previously thought. And recently, in 2023, public-private action statement launched in COP28. We will foster the technological and infrastructural solution necessary to supply the world with sustainable, safe, stable, and affordable hydrogen energy. The world knows that already. If we want to solve this greenhouse gas emission problem, we need to move to hydrogen as an energy element and a sole source of energy. And as I stated earlier, the window of opportunity is closing fast for any meaningful action to limit the planet increase in temperature and to counter the global climate crisis. Policymakers have already increased their effort to reduce the elimination emission in all economic activities. Options that would deliver only partial emission reduction, they are not sufficient and they cannot be accepted. So the full decarbonization of sub-industry and transport subsector is technically and economically challenging, and the current number of solutions is limited. These are known as hard to abate sectors. There is common solution for some of these hard to abate sectors. Hydrogen produced with renewable energy, also known as green hydrogen. Supply energy at affordable price. Can you hear me? Can you hear me?
Yes, sir. We are audible to you.
Yes, because my computer get disconnected. Just a minute. Okay, never mind. It means PC is connected, so I will go like this. So this first dimension is safe, secure, and reliable energy. Second dimension is supply energy at affordable prices, and third one is assuring sustainable development. So these are the three rudiments. And this future green energy system, this will involve massive changes in technical and organizational level, together with tremendous technological upgrade in different sectors, ranging from energy generation and transmission system down to the distribution system. These actions constitute a huge science and engineering challenges and demand for expert knowledge in the field to create solutions for a sustainable energy system. And this must be economically, environmentally, and socially viable while meeting high security requirement. So we can see here that we people from academic world and the industry, they are having larger challenges in order to meet these goals and to contribute for future clean energy system. Then question comes that what is the secure in green energy source for next generation? So if we look on some numbers, and these numbers are terawatt year per year, kilowatt hour, so hour to days, days to month, month to year, and kilowatt to megawatt to gigawatt to terawatt. So if we see the annual world energy consumption in 2009, it was 16 terawatt year per year, and it will going to increase by 25%. In 2050, it's expectation it will go to 28 terawatt year per year. And if we, how can we achieve it? So with total terawatt year, we are having coal 900. So there, it is only for 30 year maybe or so we can achieve. We use it. Uranium 90 to 300. So it is maybe 3 to 10 year. And similarly, natural gas 215 terawatt year, oil 240. So everything we cannot sustain beyond 2060 or 2070. So what is the source? So hydro, it can only meet partial requirement 3 to 4 terawatt year. Similarly, wind, it's 25 to 70 terawatt year per year. So this can have a potential candidate. Whole world can feed with the wind, but it 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 is having technological challenges because we are limited with the availability of wind, and this technology is still a single unit is still up to 15 megawatt. So we cannot make a big single unit plant. So then we need to use the park, and it's having its own challenges. But the solar energy, that is having 23,000 terawatt year per year. So if you look on perspective of bubble, they are on the whatever the energy need, or in a scale of uh, terawatt year. So this bubble is also equivalent to that. So we see that solar is sufficient to feed us for many centuries. And good thing is the price per watt of solar PV that is reducing drastically. So it's from how many fold? 15-fold it reduced in last um, like 15 years. It is 0.5 US dollar per watt. So that's a cheaper than installation cost for the coal plant. So if we see carbon neutrality, then we find that coal, if it is having per kilowatt hour 1 kg carbon dioxide, wind is having 10 gram carbon dioxide per kilowatt hour, and photovoltaic has 40 gram. So solar is having little more carbon footprint compared to wind, because of the solar panel and production and other things, they involve carbon. But coal, compared to coal, they are 100 times, and uh, you know 20 125 times lower. So what are the recent trend in wind energy system? This is the fastest growing source of new electric generation in the world, and it is expected to remain same.
And at the end of 2010, the installed wind capacity stand 2010 it was 200 megawatt, but end of 23 it will be 900 megawatt. So 900,000 megawatt, 900 gigawatt. You see that within 13 years it goes to 4.5 times. So world is observing growth rate more than 10% each year. And today 7.33% of world electricity comes from the wind power. India is also rapidly growing in wind energy production. Our indigenous technology from Switzerland that is having 3 megawatt single unit, and they are working on higher unit, higher power size unit, and proportion between solar and wind, that is not equivalent, but effort are going on to increase this percentage of wind energy in India too. And as you see that in the recent budget of finance minister, they earmark a huge amount of money for offshore wind plant, because that is the future. So if you look on this electricity capacity trend in wind energy, you see there is a exponential increase year by year. And we see that offshore, top portion in light gray, that is offshore, and this dark gray, that is conventional onshore. So, but we see that offshore proportion is also increases. And as you know, the beauty of offshore is you need not to use the land. You, whatever the disadvantage of the wind energy production, that not associated with offshore. So there is no noise, no pollution, no land misuse. And on the other hand, availability of wind is highest in the offshore. And we can already having existing infrastructure for carrying doing this offshore gas and oil rigs. So these technologies are quite mature already. So this offshore wind with green hydrogen production, that might be a future solution for securing the green energy. This is electricity capacity train, that how this electricity capacity is building in India. And you see that from tiny number of 22,000 megawatt to it increases to more than 40,000 megawatt this wind energy in India by 2022. So these are the recent trend in wind energy, harnessing wind energy for electrical power generation in area of great research interest. And during the last 2 decades, the single unit wind turbine size increased from 20 kilowatt to 14 megawatt, and even higher wind turbine size is under investigation and technological development. A lot of different concepts have been developed and tested. One important development is on electrical machine and generator, and where new concepts are also industrially implemented. And an important issue for wind turbine is efficiency. Efficiency is important when comparing different systems, because losses reduce the average power produced by the wind energy converter, and therefore they reduce incomes. I can give you example for 15 megawatt single unit turbine, wind turbine. The total losses compared to generator losses, converter losses, and auxiliary system losses, they account around 8%. And this is around 1.2 megawatt out of this. So that is a huge loss, and 1.2 megawatt energy. So there is a big potential for research. How can we do the sector coupling? How can we harness this energy loss, this excess heat? Otherwise, we need to do the cooling, and then we need to use the electricity, extra electricity, then turbine. Although it is 15 megawatt, but output is reduced. So for researcher, it will be a big research question, and there will be a lot of new innovation will take place. For example, this seawater that can be used for cooling of this wind turbine, and then carrying this heat in terms of in water molecule, and use it for district heating or some industrial use. So there may be, or we can use this heat to uh, to energize the solid oxide electrolyzer, and which work on the heat and electricity both. So we can increase the efficiency of electrolyzers. There are many ideas, but we see that world trend is uh, towards making efficient wind turbine and converter system. Also obtain maximum power output for varying wind speed. So technological focus will be on that. And wind turbine and generation adoption should be also taken into account. The generator choice is based on turbine size and wind class. This is green energy overview, world versus India. So top one and down one, we see that how the different energy sources type, and what is their contribution and how they grow worldwide. But and in the downward, we see the India growth, and they follow the pattern. Even top one is the top pink is the solar one. So we see that whatever the world, in what percentage world is growing, India is also growing in different graph here, percentage wise. So we see that we are growing economy, and our industrial revolution is going on, and we are rapidly increasing our manufacturing plant, and that's demanded on the coal and gas fire station. So they are increases a little bit, but we see that significant increase in uh, solar plant. You see that there is a in last uh, 10, 7, 8, 10 years, there is a we are following world trend, or even we are better than world trend. So why green hydrogen? When we talk about this achieving this zero greenhouse, reduce greenhouse gas emission, that it was predictable in past that green hydrogen should receive a new wave of attention from government, policymaker, energy sector stakeholder, and even the general public. And it is true now. You name the country, they are having a specific green hydrogen policy, and we are fortunate. In India, our Prime Minister make this green hydrogen policies around 4 years back during Corona time, and we are leading in some of the part, and lot of startup they are started, and I was reading somewhere that India will bring 21 hydrogen train by next year. So Indian Railway will adopt 21 hydrogen train, and we already heard about hydrogen car, and we already seen that there is a bid for government subsidy for bidding electrolyzer plant, and there are more than 2,000 crore rupees subsidy for that, and there are big players they are coming for producing hydrogen in India, and specifically green hydrogen. An unprecedented number of report, news article, webinar, and event in the last 2 years that touched upon this topic. And please note that this hydrogen, it is not something new. We are producing 120 million ton hydrogen globally. So the supply chain and and the ecosystem, how to store it, how to transport it, how to use it, what is the safety measure, and all those they are already placed very well. It's the only question how economically efficiently we can produce green hydrogen. I mean, using the renewable energy, and uh, using and feeding the electrolyzer plant by this renewable energy, not a coal base of or gas based electrical energy. So there we need to increase the efficiency, as electrolyzer plant are not more than 60% efficient, 65% efficient. And similarly, there is a some challenges with per unit cost of renewable energy. depending on availability of wind and sun. So this is, very good, good news and good knowledge that the ecosystem and infrastructure behind hydrogen to handle the green hydrogen is already well placed in India. Like cement, this fertilizer industry, chemical industry, petrochemical industry, steel industry, they are using hydrogen as an element, but they are using brown hydrogen or black hydrogen, not the green hydrogen. That's the only question. Like 75% hydrogen consumption goes to crude oil refinery and ammonia and methanol synthesis. And recent geopolitics and energy crisis that paved the way for faster transition from green hydrogen. So there are certain other, rationales why green hydrogen. So International Energy Agency predict by 2050 there is a larger, greater dimension than today for use of green hydrogen. So there is a 400 megaton hydrogen is required, 5 terawatt of energy, and electricity demand to produce hydrogen reaches close to 21,000 terawatt hours per year. Achieving these ambitious numbers will be a major challenge, but this challenge can be met through a wide range of policies and networks. After geopolitical issue and pandemic, green hydrogen has already received a new wave of attention. And EU, US, India, China, they are all in action. This arena World Energy Transition Outlook clearly sees the green hydrogen has the most important role. So being said that, and then with this conclusion that in order to meet the green hydrogen as a measure for global greenhouse gas emission reduction, how hydrogen can act as a energy storage element, what are its properties. So as we know that it's the world lightest and tiny molecule having only one electron, and its melting point is 13.81 Kelvin and boiling point is 20.28 Kelvin, very close to absolute zero, around minus 252 or something that degree centigrade, and its density is 0.0898 gram per liter. Electronegativity is 2.1 and ionization potential is 13.59 electron volt. So there is a mystery, color of hydrogen. We say sometimes blue hydrogen, black hydrogen, green hydrogen. Nothing. It is nothing. It is the way we produce the hydrogen. So if we use the coal or pyrolysis, natural gas, then if we use hydrogen produced from natural gas with chemical process, then that is a gray hydrogen. This gray color. Blue one, if we use the steam methane reforming method, which is the industrial method, and so then we produce hydrogen, that is the blue hydrogen. Brown one, when we are using coal gasification for producing hydrogen. Green hydrogen, any type of renewable energy, whether it is geothermal, solar, wind, or biofuel, or whatever. If we are using any type of these energies to feed electrolyzer plant, then that energy, that hydrogen produced by electrolysis is known as green hydrogen. But if you use the specific solar energy for electrolyzer plant, then it is green hydrogen and yellow hydrogen both. More specifically, you can say that it is yellow hydrogen because it is subcategory of the renewable energy. White hydrogen, if we are having a geological trace underneath earth, then deposits, underground deposits, and hydrogen available as a solid white material. There, and we produce hydrogen from there. That is white hydrogen. And pink one is when we are using nuclear plant to feed the electrolyzer plant and produce the green hydrogen and the hydrogen, that is the pink hydrogen. And please note that this pink hydrogen is, although it is pink, but when we say the green hydrogen, then this is also comes in the broad category of green hydrogen, because nuclear is also considered in that category. So these are some interesting number. Energy density, you see the hydrogen 141.8 megajoule per kg, and liquid and gas, they both have the same, because it is the weight basis, the volume is not considered, and it is almost three times more than methane and gasoline petrol. But megajoule per liter, you see, it is again 3.5 times lower than gasoline. So in gravimetric energy density is higher, but volumetric energy density is lower, and specific gravity is low. It is 0.071. It's 10 times lower than petrol or gasoline. Melting point, boiling point, we see, I told you, minus 252.8. And carbon dioxide emission, this is 0, because when you burn it, it produces water and there is no carbon dioxide. But gram per megajoule, we see 148 with gasoline and 111 with the methane. And flash point is not applicable, but there is a flash point with the gasoline, petrol in 13.3 degrees centigrade. So it makes safe hydrogen from point of view of flash point. So what, on a weight basis, hydrogen has a high energy density, around 3 times. But on volume basis, it is having 1/3 energy density. So as a whole, 1-to-1, we compare and we can say it is equivalent to, or not too bad compared to gasoline. And liquefied hydrogen, that is currently used in special application as the space industry and space mission, and in such cases issued to do with thermodynamical efficiency are not critical. So for space, if we are using extra energy to liquefied hydrogen, then the energy density further reduce. But this is not issue for the space industry, because this is not a bottleneck, and it's a few penny in the whole project, the liquefied cost and energy reduction. But if we talk about mass use of liquid hydrogen, then this is one of the bottleneck. The energy used to liquefied hydrogen to maintain liquefied state, it involves a lot of energy, and that reduces further energy efficiency of hydrogen as a fuel. So this is somehow not encouraged. So while we see that volumetric density of gaseous hydrogen at atmospheric pressure is 0.09 kg per meter cube. So in 1 meter cube tank, we can keep 0.09 kg hydrogen, and it's not viable, and it's not a practical thing that we can make a huge storage for that. So we increase the pressure. Normally practice is 350 bar and 700 bar pressure. Heavy duty vehicle, they 700 bar, and light vehicle 350 bar, and vice versa also possible. And there, this energy density, volumetric density of compressed hydrogen is increased to 10 to 15 fold. At 350 bar, it is 26.1 kg per meter cube. So 1 meter cube store 26 kg hydrogen at 350 bar, and it is enough for 500 to 6 kilometer range. And at a pressure of 700 bar, it is 42 kg per meter cube. So please note that it is not linear, but it is increased. With the Hyundai Nexo, 125 liter tank contain 5 kg of hydrogen, and it is a product already available in the market, and it can drive 600 kilometers. So liquid hydrogen is strong candidate as an energy carrier for sustainable truck and aircraft, which are currently under development. Because for sustainable trucks or heavy duty trucks, we need more energy density and long range. So, and that is not possible with even the compressed hydrogen. These are some comparison how volumetric versus gravimetric energy for different gases and uh, energy sources. And we see that hydrogen lies in the right corner where a lot of gravimetric energy density, but it is lacking in volumetric energy density. But as soon as you increase the pressure, you get some volumetric energy density. And liquid hydrogen, it is highest 10 megajoule per liter. And it is the comparison battery energy, electrical vehicle energy density in volumetric versus gravimetric. This comes here in this range, gaseous fuel here, and liquid fuel here. So hydrogen lies in this corner. We can compare that weight-wise, hydrogen having a lot of advantage. So it can make the application light compared to battery. But batteries are uh, they are their gravimetric energy density is poor. This is production value chain of green hydrogen. So we need to use the renewable energy and then electrolysis, and then we need to carry it by a dedicated corridor of pipeline or connection to industry, or we need to have a fleet of transport vehicles and tankers which can carry safely hydrogen from one place to another place. So production can be through renewable energy and different sources. Then transport can be by shipping, by trucks, by pipeline, or by storage. And transformation, then without transformation, we can pass in to application, or with transformation with sustainable CO2 capture, we can produce synthetic fuel like uh, e-ammonia or e-methanol or other e-fuel or green ammonia. We can say it's green ammonia. And end user can be industry, so steel industry, chemical industry, refineries, cement industry, fertilizer industry, transport sector, shipping, aviation, car, rail, trucks, and buses. And we can use it for district heating, and as well as we can use for power generation, although efficiency is lower. But in extreme cases where we don't have availability of power grid, as well as uh, costly battery energy sources, and concern with carbon footprint of battery energy sources, storage, we can use hydrogen for power generation. So this is another picture showing you role of green hydrogen for decarbonization of energy production sector. So you see that large scale efficient renewable energy integration, we can do it. We can then distribute energy across sector and region by production of hydrogen, and act as buffer to increase system resilience. So we can store in this hydrogen, and we can use hydrogen as energy use, but on the same time we can connect our grid through fuel cell in case of any deviation in power demand that can be locally met through this buffer. And it can use, as I told shown in previous slide, it can decarbonize transport sector, it can decarbonize industry use, it can serve as feedstock for fertilizer industry or cement industry or some chemical industry. And this also help to decarbonize district heating or building heating. So if we look on for hydrogen is the new heavy duty fuel. It is 100% clean and reaching diesel parity. Technology is proven to commercialize green hydrogen. Power generation, hydrogen production, hydrogen distribution, and hydrogen stations. Then we hydrogen fuel vehicle. There is this hydrogen station. It is having its own challenges, but again the good thing is the supply chain and infrastructure from CNG in India that can upgrade it to meet the strict challenges of hydrogen station. We need more safety. Our 200 bar pressure need to increase to 700 bar, and then of course compared to CNG, hydrogen needs more safety. So safety concern, safety standard, safety practice that need to be upgraded. This is another perspective, and time is as going very fast. So I will not go here. I will directly go to comparison slide where I can give you new insight why why we need hydrogen. So if we are talking about battery energy vehicles and we are talking about fuel cell electrical vehicle. So battery electrical vehicle, they are reality. We see that a lot of BEV produced in India. There are many players, they are making it, and it's growing penetration in the use. But it's fuel cell electrical vehicle. There is a prediction from global statistics, global market insight, that is, its market will rise with a cumulative average growth rate of 25%. And it is a more than $30 billion market by 2032. And please note that this short distance segment, this automotive segment, car segment, that might be only 1/3, 35%. But the short distance segment, like fork truck or forklift or agriculture equipment and off-road vehicles and this type of applications, they will be dominated by the hydrogen uh, fuel cell vehicle more than 90%. And Asia Pacific is also having it, although it's a US report, but they predicted for Asia Pacific region the same cumulative average growth. As a very superficially, if you look on battery energy, battery electrical vehicle and fuel cell electrical vehicle, then charging refueling time, that is compared to many hours to few minutes for FCEV. That's a major advantage. User will not have a cultural shock or change in his daily practice. He will have the same experience like what he's having today. Safety is there were some comparison, and in case of fault, in case of leakage, in case of fire, hydrogen can, because of its lightest element, it disappear quite fast, and compared to battery in fire hazard, it is more dangerous. And cost wise, it is technological challenges are there in order to have a sustainable supply chain from production to distribution. So it's more, but in future it will reduce. And then well to wheel emission, it is the lowest for FCEV, because when we talk about battery electrical vehicle, then we cannot guarantee it is green energy. It is e-mobility. We are not doing pollution, but in order to charge that battery, we use the national grid, and national grid is still having, as I showed you earlier graph, it is 70% energy or more than 70% energy that coming from conventional sources. So that is not clean. And these plant, gas plant and coal plant, they are having efficiency, marginal efficiency, 20%, 25% or less than that. So we are not green there. But with the green hydrogen, we make sure that we are not using any polluted energy source to produce it. So that is, and then if you compare the full well to wheel efficiency from coal plant and gas plant till battery in electrical vehicle, then you can find that there is a 2x increase for fuel cell electrical vehicle. This efficiency, it's around 32%, and for 30 to 40%, and for battery electrical vehicle, it is 15 to 20%. This is a specific energy comparison. As I shown you graph volumetric, gravimetric comparison. You see that. So lead acid, nickel metal hydride, lithium ion, and United States, this battery consultancy they develop some new type of batteries. So you see that there is a watt hour per kg for 5000 psi, means it is um, 350 bar, and this one is 700 bar pressure, and it's quite high compared to battery. Same if you look on weight of battery electrical vehicle and fuel cell electrical vehicle, it is per range. If you increase mile range to 400, you see that hydrogen fuel cell is not increasing weight, but there is a exponential rise. Any type of battery you use, some are non-viable. You cannot use them like lead acid or nickel metal hydride, but lithium ion can be used. But it is compared to hydrogen, it is how many? 3 times, 4 times more weight consuming. This is energy density of hydrogen based fuel cell electrical vehicle and battery system for BEV. So this energy density watt hour per liter. Then again we see that hydrogen superpass, and it is having better perspective. This is volume of hydrogen storage and battery systems, how much volume involved in it. Energy storage system volume. And again, we see that fuel cell hydrogen tank and Department of Energy has to storage goal. It means it's report taken from US Energy Department, and you see that this is the goal, but we are having this these dotted curve for 700 bar pressure atmospheric bar, and it is also a huge saving compared to battery energy vehicle. This is another way to look into specific energy versus specific power. When we talk about specific energy, then it is mean for range, and specific power needs terms of acceleration. So we need a bigger kilowatt motor, and then we need a bigger kilowatt hour capacity. And look into these fuel cell, they lies here and in a good position compared to lithium ion battery. They are good in watt hour per kg, but not in specific power comparison. And this BEV goal is we need this 150 watt hour per kg and 300 watt per kg power. And comparison to this, we see that fuel cell surpass again this need for a specific range and acceleration requirement of e-mobility. So this is well-to-wheel greenhouse gas emission, and lowest is for fuel cell electrical vehicle. It is gram per mile. It is coming around 200 gram per mile for greenhouse this green hydrogen based battery energy this fuel cell electrical vehicle compared to battery electrical vehicle. If you look gasoline, then our lithium ion is for longer range. It's worse than that in terms of greenhouse gas emission, because carbon footprint of battery manufacturing, that is a big factor, and we forget about it. So and disposal of batteries, and it is not a sustainable solution. So that's again giving better advantage and better perspective for fuel cell electrical vehicle. So I think my time is already over. So I will go through my conclusion. So what need to done? Increasing the penetration of intermittent and zero carbon generation sources, increasing the stock of FCEVs, and subsidizing capital investment in energy storage project, because there is a lot of technological gap, And in order to meet this gap, this capital investment and subsidy that should be there. And our conclusion is the fuel cell EV is superior to advanced lithium-ion battery full function EV on 6 major count. Weight is less, take up less space, generate less greenhouse gases, cost less. And when I'm talking about cost, then the lifetime cost, because battery is limited for 10 year or 8 year and battery life. And then if you look on the cost of BEV, then it is around 50 to 60% cost. But whereas in FCEV, this hydrogen tank, it is having not more than 2 to 5% cost. You can replace it and you can use it again. And fuel cell is a repairable, and it is a sustainable approach as compared to battery. Higher well-to-well efficiency and takes less time to refuel, so user have the same experience like conventional gasoline-based car. What are our key takeaways? The global mega trend shows that green energy shift is happening, and innovation in e-mobility through green hydrogen technologies, that is the necessity of today's world. And harnessing advantage of full value chain of green hydrogen is an essential component in the success journey of green energy transition. Being said that, I say thank you so much for your patience. And now I give floor, I request to organizer for 5 minutes more for any question and answers. So now floor is open. Please ask your questions and doubt. And before asking, please tell your name and affiliation, which institute you belong. Dr. Arnav? Are you able to hear me?
Yes, sir.
So this is now times question and answers, because I was supposed to give only 1 hour lecture, isn't it?
Yes, sir. Yes, sir.
So my time is over, and you have not pointed me, but I know that participant, they are keen for next lecture. So I request you for 5 minutes and ask. Floor is open for any question. If anybody is having any question, any doubt.
I request all the participants to put forward their queries. Any queries, participants? Okay, then we'll conclude this session. Thank you, sir. Thank you very much for throwing this light on this topic. The participants were really benefited by this one. Thank you very much, sir.
Thank you, madam. And I say once again, thanks to organizer and thanks to participants, and thanks for this opportunity.
Thank you,
Take
sir.
care. Bye-bye.
Thank you, sir. So participants, we'll start our next session at 11:30 with Indrajit Sarkar, sir, NIT Rourkela.